Excellent. Good morning, everybody. This is Kevin Hanley with Computer Aided Technology. Just so you understand the logistics, Tim Crennen and myself are at our Denver office where we have a desktop metal studio system. We'll just start by just doing a quick overview. We'll get into some system specifics and show you the system, as well as go over some applications. And I'm going to pass the ball over to Tim.
All right. Yeah, so jumping right into it, we'll figure out a little bit about two different metal 3D printers that are out there and how they work and what specific applications they are better at. There we go. So a couple of different things we'll jump through real quick for, promises of metal 3D printing. And, bring a whole lot of things to the table. So we have rapid prototyping, obviously one of those where you can print out parts out of real metal. But also allows you to do things like part consolidation, and that kind of goes hand in hand with complex geometries, where when you're taking multiple parts and consolidating them together, we're making complex geometries. And you can also do unique geometries that people weren't looking at previously because they weren't manufacturable or easily manufacturable. Also allows for things like design customization, where we can make one-off parts really easily, do a lot faster iterations of metal parts for metal prototyping and all that. Rapid tooling, where if you need to make stuff, we're actually working on factory floor. And these are, kind of fall into the one-off category of parts where they have unique geometries. You don't need a whole lot of them, but you need them quickly to get things up and running. Things get broken, you can get quick replacements with on-demand manufacturing. And that applies for, on factory floor or just one-off parts where you have like an old housing for collectible cars or something. You need to make a new metal part and just manufacture it right there. You don't have to build up a whole, lost wax casting or investment casting or anything. And then also supply chain engineering. It's a big one everybody likes talking about nowadays with the whole COVID situation, realizing that, chinks in the armor, seeing what's going on it's causing big delays and slowdowns. Now you can bring it all in-house and, have the end-to-end solution from designing parts to getting end-use metal parts, and not having to have any entire factory full of ancillary equipment. So with that, we'll jump into looking at the studio system at Desktop Metal and how specifically this machine works and our layout. So we're going to jump to the webcam right now and actually show in person what these look like. All right. So hopefully you guys can see me on the webcam here, and we'll take a look at these machines back here. So behind me we have all three of the machines, which is all you have for the whole process. And it's all very office friendly for the setup. In the middle here, we pretty much have the printer apparatus side of things. So, it's got flat, easy. This is a low temperature outside of the application, so there's no high heat involved. It's actually just an extruder that's extruding metal powder out that starts out in raw form. We end up with something like this, and they come in hot swappable cartridges of material. So you have containers like these loaded up that have a whole bunch of rods of the filament. So this is the actual metal filament here that we're going to be printing with. Much safer and easier to deal with than metal powders. We don't have to have any hazmat suits, as you can see. We don't have to have any special handling procedures. We're not even wearing gloves. And those just load up here, so you can have multiple bays loaded of it, so you don't have to worry about running out and coming in and swapping down mid-run. Now we just hit print, and it works really similar to an FDM style machine, where it's actually heating up the tips and melting the metal polymers and binders in the rods, and not the metal, and actually just forming it into a general shape. And once it gets printed, we end up with a part like this. So this is just straight out of the printer, uncured, soft part. It's kind of the consistency of like a crayon. You can scratch it and dent it with your fingernail at this stage. Then what we do is we take it from there, we put it into the debinder set. So the debinder is over here. Hopefully it's still on screen. And basically this is a chemical bath that we put the parts in that removes the binder agent from the printed part to get it ready for the sintering process. So the cool thing about that is that it can be batch processed for the debinder and also for the furnace, which lets us do a little bit higher throughput on those. So if you have some situations where you're doing short run production or something, you can actually get the setup where you get 2, 3 of the printers, print out parts, and you can take all the parts you printed, batch process them on the debinder at the same time, and then take them from there. And then you batch process it there, and then you can take it from there and put it to the debinder, and we'll bring it to the furnace. Well, I'm going to actually open this on up so you can see what the deal with that is. It's actually a decent sized machine, but you can see all three of the machines fit right here in one frame and are in our office environment without needing any special equipment. And so this is the actual furnace that heats up the metal parts and sinters them down into a solid, dense metal parts for end use. And then the other aspect of what it reuses is when it's printing, the support material actually gets laid down with a layer of ceramic material between the parts and the support. That way they don't fuse together. So there we go. So because the support and the actual model don't fuse together, you can't really see it on here because it's such a thin boundary layer. Kind of show you on this one. There's a little white line kind of in between this base plate and the actual part, and that's the interface material. So once we put it in the furnace to sinter, that powderizes down into a ceramic powder, keeps the two parts from fusing, and then when we take it out, we just drop it on the ground, and then we just drop it on the ground and basically separate the parts. So here's the furnace. All the parts fit in here, and again, it's going to be batch processed. And you take your parts and you set them on ceramic setters within inside here and inside our graphite retort. And then it has a bunch of high temperature heaters in there, and we run that. And that takes about 48 hour procedure to run through the whole sintering. Ramps up the temperature, then controls the cool off. Actually, the whole thing is ran under an inert gas combined with vacuum. So depending which part of the cycle it's in. And because of that, it's actually a much more efficient process too, because we're not doing a constant flood of inert gas into the chamber all the time. And then one of the other advantages is that all this is controlled by the Fabricate software. So you don't have to be an expert. You don't have to be a metallurgist to do any part of this application. You don't have to know anything about generating supports. You don't have to know anything about the different material properties. The software handles everything, and it's all connected together through the cloud. There's also an offline version into the software. So you take our part from CAD, which can take native CAD data, and then we send it to the printer, it prints. We send it to the debinder to get debound, and then we send it to the furnace, and it sinters it. And it controls all the processing time, cycles, durations, and we don't have to know anything about any of that to get these full strength mill parts.
A couple of quick things I just wanted to point out. First of all, I'm sure you've all noticed that this is an office environment. In terms of venting, we have one small tube that vents out inside the building. Office friendly, we don't have explosion-proof canisters around here. This is something that we are literally surrounded by our co-workers' offices right now. Second thing, which Tim's mentioning, is the release layer. We don't have to worry about grinding a welded part off of a build tray, which is what happens traditionally for metal 3D printing. So there's some distinct advantages to being able to keep this close to your design centers, close to your engineers, not in the back of the shop with a lot of peripheral equipment and safety and environment concerns. I really want to point that out.
All right, so that pretty much is a quick overview of how the systems work. So we'll go ahead and jump right back into our PowerPoint, show a couple more slides there to get some point across, and then we'll jump back into looking at a whole table of parts here that we'll be taking a look at, including, putters. So jump into our PowerPoint. So here's a bigger show of the separating the support from the actual model, and this really shows the difference between the desktop metal supports on the right and traditional metal 3D printing with metal laser sintering. So on the left, the part's literally welded to the tray. You have to get grinders and everything cut it off. You can see on the right, with the ceramic powder in there, the parts just separate by hand. You don't need any fancy ancillary tools. You don't need EM machines, grinders, any of that stuff. Parts just come right apart. And the software actually generates support material. Specifically, will recognize if it's going to be in a captive region and make it into its own separate section, so they will follow the pieces that come out. So it's a very user-friendly and intuitive way to do things. So jump right into some applications here. So this is a pretty neat application for some larger parts that are made by a company in Italy, UWOL, UWOL. So, they were founded a while ago, 97, and basically they do high-end, yacht propellers. Kind of the things you'd expect out of Italy. We got some, high-end luxury goods. But what they're doing with these propellers is that they have a very unique connection because they're actually able to control the angle of the propeller blades, like on the fly while using it. So they have a, interesting connection pinion onto it that is very, pretty costly for them to actually make. And they're, making it out of investment casting of 17.4 pH metal, which is one of the exact materials that we can 3D print on the studio system. We actually have a array of metals from 17.4 pH. We have 316L. We have a couple others in development. We also have some tool steels. But what they're able to do is take this part, and this is actually a big part. So this thing's like, I want to say, 10, 12 inches tall, and, pretty decent diameter. And instead of having to cast that thing and then do some really expensive machining operation with multiple setups, having to go deep down inside of this thing because it's hollow and machining out specific recesses for it to attach, they can 3D print it to, near net shape and then go in and machine critical features after the fact. So on the right of that picture, we have the straight out from being sintered. And then on the left is when they did post-machining operation. So not over the entire part, just in the areas that it needed it for critical surfaces. And then you have a finished part, and put your threads in because it's a full strength end-use metal part. You kind of see some more views from there. You can see the inside deep wells on that would be very tricky to try and CNC machine all the way down there. And so that picture on the left there is actually pretty interesting. So there is a lot of shrinkage involved when you are sintering metal 3D parts. So this is all, a pretty well understood situation. So this is heavily based off of metal injection molding industry's technology. And they have been doing this for, a lot longer than metal 3D printing has been around. And that has, it's very well-defined amounts of shrinkage. But you see those two size parts in that left picture. The larger one is what it looks like off the printer. So it's printed oversized. And again, this is all taken care of in the software. So it scales the part up, prints it oversized. And then once we debind it and put it in the furnace, it actually shrinks down to within high accuracy of the near net shaped part in the end. So all that shrinkage is built into the software, and you don't really have to factor in any of those calculations. But basically, this ended up being a very good thing for them, where they were able to get all kinds of benefits from, less labor-intensive parts, lower cost parts, obviously, but faster turnaround times, less demand on logistics, where they had to worry about specific long sizes they might need. And so they're, definitely looking into that for, more things they can do with it in the future, and also exploring some ways to use it in the shop system, which we'll learn about a little bit after the studio system for doing some higher volume production. Another example would be the Edgar Tool and Die from Canada, and they do a whole series of different things. So they are a manufacturer of basically whatever needs making. So it's a very broad scope for their business applications. And when they're looking to take projects on board, they look at 3 key criteria, and if it meets 2 of them, they say, all right, this is a good criteria to bring in and start applying it to our operations. And they had some, a bunch of really unique situations they applied it to. This one I thought was pretty fun because it seems to kind of go the other direction when what a lot of people are thinking that's going. So they're actually able to replace a nylon part with inserts in it to a 3D printed metal part. And the 3D printed metal part does metals a lot stronger and more durable. They're able to get much lower head profile for the size of the tool, and also make it cheaper and lighter, because once you bulk up all the amounts of actual plastic nylon you need to make it strong enough, we can compensate for that with metal much easier and quicker. And you can optimize your design, and you don't have to worry about how much material you're going to have to cut away to actually machine it down from a big chunk, because we're just 3D printing it and only getting what we need. They're able to use some H13 tool steels to make stamping dies and extrusion features. And then this one's kind of neat. So it's optimizing a servo-driven timing belt. And basically, this is it's a big thing, and it spins around on a belt. They have a big servo driving it. When it's currently how they were making it, it's solid aluminum, and it's very heavy because they all chunk of aluminum, not optimized at all. So they were able to make that design on the right picture there by optimizing it and dropping a whole bunch of weight out and printing it. And this makes sense because it's actually a fairly large part. You can see the side of someone holding it. That's going to have a lot of metal weight on it. We can drop a lot of mass out of it. You'll be able to spin it a lot quicker and a lot more control with the same size bolts or servos. And they're also jumping into looking at some other things. So copper is the one that they're working on coming out with for the studio system. And they're making some custom, conformal cooling electrodes out of copper, so they can actually build cooling channels directly into these parts. And this is something that they use a lot with, like the tool steel. If you want to make small injection molds, pre-print it up, you can polish the surface to whatever finish you might need, and then they can actually build cooling channels inside of the part and make it, have a much longer shelf life, a lot number of iterations to get out of it. So obviously lots of good business impact, especially with all the varieties of materials that they can access through the machines. So Turner Motorsports is a neat one that also shows another aspect of cool software that Desktop Metal offers. And basically it's a leading BMW tuner and race team in North America. And what they were looking to do is take a V8 engine, get a new modern V8, pop it into their 2001 frame. But that comes with its own challenges of having lots of different geometries you have to meet. So they were able to use the Desktop Metal Live Parts generative design software to build a part for them. So what they did is you go in and you 3D scan using a freeform scanner or something like your engine bay. You get the exact areas of where, okay, here's my mount holes, here's my restrictions for areas that a part has to fit through. Here's the other area has to fit. You put in some other parts for headroom. So give the constraints of what it has to work with, and it'll literally grow apart to fit around all of those pieces. They're able to go through several iterations of design, looking at different performance criteria and also other rooms. So it might be blocking a bolt, even though it's not touching the bolt, they can access it. And then they came up with their final design, which does two separate pieces that they would then weld together. You can see the weld spots here, the top and bottom. And they were able to 3D print that and get a perfectly fit design that goes around all the complex geometries that already existed there. You kind of see this picture of the engine with the mount right there in the middle, kind of snaking its way past all the restrictions, constraints, and getting around difficult areas, perfectly fitted to the spot. There's another view of that. And they're also able to do a couple other things like, we need a sensor housing. Just model it up, 3D print it, have a metal one. There we go, one-off sensor housing, great for race situations. You can see it over there on the right. But obviously, when it comes to racing, being able to shave months off your production time and get things up and running, optimized quicker is a huge benefit.
One thing to consider as well when you're looking at organic or topology optimized parts is they are very difficult to traditionally manufacture. And that is where 3D printing comes in. Just like it does with polymers, it does the same with metal. And we are able to get forms, shapes that were just pretty much impossible to make prior, which opens the door for design creativity and iterating in directions you never would before.
All right. And then, so that just gets us to talking about a couple other less in-depth case studies. We'll be able to show all the parts we have on the table here. So we have a whole series of stuff on our table here. So first one is little end effectors we were kind of talking about earlier, but this really shows the difference between traditional manufacturing costs of some complex little end grippers. That's things like these little guys here. So it has specific unique shapes in the front, but it also has other stuff. So we've got like holes coming down here, holes on the sides, different cavities on the bottom. So these can make for kind of tricky things to try and manufacture and machine up, where we can 3D print them very easily even tiny little things that have lots of small geometries. Yeah, so I'll kind of jump between those. So here's an example of one of the putters, and basically, you can do some really cool, complex designs with this. All those internal, speed holes, whatever they have on that putter design there. But again, it can save a lot in manufacturing costs. So you see all the parts I have on the table here. And we have a bunch of whole array of stuff here, and some of them are also they've been printed, but they haven't been sintered. So again, we can show that size difference. Some interesting ones to go over. So here were the little pieces I was showing earlier for little end effectors. You can see they just little guys fit on hand. Lots of little tiny details in them. But then there's some other stuff like different nozzle designs. So this is kind of a cool flower nozzle. It's pretty complex, has a lot of different features, overhangs, got different mounts on it. This would be a very complex part to try and machine up and manufacture, especially if you're in the design stage and you're trying to figure out what's a good design and do multiple iterations. Now you can just 3D print it and get straight out the machine and do a batch process of that. So you can test 4 different examples within a week. Then that makes for a big difference. Huge kind of difference between the finished part, which is that big, and the part that hasn't been sintered yet. You kind of see the shrinkage difference on those can be stand out pretty dramatically. We can also do other parts that are really cool and complex, but they don't look like it from the outside. So this is actually a really neat part that has internal cooling channels and everything built into it. So basically, it mounts on, something's going through here to be cool, and you have your inlet and outlet right there on the front. It actually has spiral tubing wrapping all the way down through this part and then coming out. So there's internal filling in there. So it's actually able to cut away the outside of it, so you can actually see all the internal spirals going through there. You also get a little bit insight into the actual structure. So when the parts get too thick, we don't print them completely solid, and you actually have a little bit of infill. So this kind of shows that's that same part, but it hasn't been printed yet or sintered. And you can actually see the kind of sparse infill that we have on it. That's similar to what we do with like an FDM machine. When you want to do sparse infill on a plastic part, we do the same thing with the studio system metal part. Questions you guys might have. So we have things like color design, which again, when you look at the traditional cost of making something like this, which can be very complex, lots of unique curves and geometries. You can see the cost difference between traditional manufacturing and DM costs, where $2,000 with $50, pretty big difference. And again, these are full strength level parts, so we can do that for end use. There's that flower nozzle we were talking about earlier. That's a pretty decent sized part. So once you factor all in, it's about $200, but compared to how much it would cost to make something like this, or even if you couldn't because the geometry was just too complex. And then also getting down into the unique geometries of generative design, and it's really complicated situations where nobody would have even thought of machining these or making these that way previously. Now we could just 3D print whatever the most optimized design is and make that a reality and not have to compromise between practicality and optimization. But with that, I think we're getting close to our end of time for our studio system here. So we can jump ahead to ask any questions anyone might have.
Okay, we did get a few questions, Tim, in the chat window. I didn't hear you mention this, but the material density when it's done, how does that compare with MIM or traditionally machined materials?
So it's the same material density in the end. So what we're looking at is about 98% dense solid metal parts, and basically that is the equivalent of cast metal parts, machined metal. You don't ever really get to 100% dense metal part unless you're doing some crazy isostatic pressing and other processes on top of that. Just regular metal is around 98, 99% dense, and that's what our studio system parts are getting.
There's a one question that's you mentioned high accuracy when you were talking about the post processing, the scaling, and the shrinkage. Do we have any statistical information associated with that?
Yeah, so the accuracy on the studio system parts is basically it's a little bit better than cast metal parts. So they call it near net shape. They definitely want to make features route on there that are going to need actual high accuracy pullouts. We're looking at around I think it's 0.8% accuracy on the parts once they're finished and sintered, and then so it gives you okay accuracy. And then if you actually need something pulled out to, we need plus or minus, 0.1 millimeters on this stuff over here, then you can go ahead and just make sure to make those proud. And you can kind of see that in the propeller design. They have made a bunch of extra material at the top and made a little bit extra thick area, so that way they can turn it down and machine it to the actual final geometries they need for critical surfaces. So, but you kind of treat it like a higher accuracy version of a casting.
When you had the generative design images up there, that looked a lot like SolidWorks, but what software was that?
So yeah, there's lots of generative design softwares out there. The one for the BMW race team, that was actually, it's literally called DM Live Parts, is their generative design software. And that works kind of backwards from topology optimization. Generative. So you literally say, hey, here are my constraints. Build a part that connects these things and meets this string. Versus topology optimization, you build your blocky part and you say, all right, here are my constraints. Now cut away material to get to an end-use part. So SolidWorks has topology optimization and DM Live Parts has generative design. And then there's other options out there too.
Can you talk about the debinder a little bit, solvent, catalytic, what's going on in there a little bit more?
Yeah. So that is it's a liquid solvent. It's not water. It's actually a chemical proprietary mixture. And then basically you pour a bunch of it in. It's all in a closed, sealed cabinet. So it heats up the liquids. It penetrates into the part. So the thicker the walls on your part, the longer it has to penetrate in. Typically you look around 12 to 36 hours for cycle time on the debinder. And the liquid penetrates in, removes the binding agents, and then it actually distills the liquid, and then takes out the binding agents from it, puts it into a waste container, and then refreshes it, and it lets you reuse the material. So it's a very effective material that you can actually reuse a bunch, and you don't have to swap out the whole vat of liquid every run or anything. You literally top off an extra, liter of the material every so many runs, depending on how much volume of parts you're running through it. But you don't have to be changing out the vats of liquid or adding new stuff very often.
Somebody's asking about the building layer thicknesses. Can you cover that, and then maybe include the shrinkage and how that affects the layer thicknesses?
Yeah. So there's two layer thickness options with the studio system. They have the regular nozzle, and they have a high quality nozzle to print the final layer thickness. So we believe standard is about 250 microns, and then they get the high resolution, it's down to 50, and so you can get some nice smaller details in there. And then with the shrinkage, you're looking at it's around a standard shrinkage around 19% in each direction. So it's pretty dramatic shrinkage, as you can see from some of the parts that are showing for the before and afters. Right, on camera. But yeah, there's those two parts. So you can see the size of it straight out of the printer versus the size once it starts sintering. So it shrinks about 20% down. And then that also helps the materials bond together tighter and get that, higher density metal parts out of it too. So any little air gaps that might have been printed in there from the process, that all shrinks down 20%. The layer thickness from what it gets printed at gets shrink down 20%. So you end up with finer resolution than what you printed at in your finished part because of it.
Okay. Can you go over the tooling steels or the tooling materials that are available today?
Yeah, so they have, I believe there's about 4 or 5 materials available currently on the studio system. And then they're constantly working at coming out with more. So there's there's 2 stainless steels, a 17.4 pH. There's 316L low carbon. The tooling steel is H13, is the main tooling steel they have. And then they also have a 4140 chrome only. And from there, they are working on coming out with very soon the copper material, and also a super alloy 625. What it's called. Those are the main ones that are in the hopper right now, and then they're going to be coming out with more. So one of the cool advantages with the studio system and also with the shop system a bit too is they are leveraging the metal injection molding industry. So that has a whole existing multi-billion-dollar industry of already engineered materials that they use for that, and they're actually using those pre-made materials and just figuring out how to roll them up into rods to put into the printer.
Yeah. We are coming to an end for this Q&A. I do have one more. If we don't get to your question today, everybody, we will address those. We'll send out an email later on. But we did have a few people that asked a time to build and a time to part. So do you have any samples that you can hold up and say it took this long to print it and it was this long before I had a part in hand?
Yeah, so time to build, time to part. So time to build obviously varies dramatically based on geometry. It's generally, you can think of it as being a little bit slower than like Stratus's FDM machine for the printing the part, and then you have to debind and furnace. So something like this part, which is pretty big, half-used solid chunk of metal, or even this guy here can show. So this would take around, say 24 hours to print or less. So you're looking at, let's say, 18 to 24 hours to print this part. And then you put it in the debinder, and that's going to take you, let's say, roughly a day. So you put it in, come get it tomorrow. And then from there, you put it into the furnace, and that takes 2 days. So if you want to just print a part, debind it, and furnace it on that single part and not batch process it, you can print it on Monday and then have it done by Friday.
Okay. So the rest of these questions, there is still a few. We're going to we'll send out a follow-up email afterwards with the answers as best we are able to. For now, we need to pass the ball over to Ilya. I'm hoping you're ready to go, Ilya.
All right.
There you are. You're set to go.
All right, cool. So you heard about office printing when you need a few parts a week. Now let's talk about the shop system where you can print a few hundred a week. So I'll cover a few of the, what's the reason for existence for the shop system and really for desktop metal, key limitations in conventional metal forming processes, and then talk a little bit about binder jetting and the metallurgy, the origin of it, and then talk about shop system with a big focus on the applications, some of the early adopters. So let's go. So what's the big challenge? The big challenge is for mass production of actual parts. So not prototyping, not tooling, but like mass production of parts, is that a lot of the mass production processes, casting, stamping, machining, molding, really require some calendar time and non-recurring engineering efforts. And so if you think about processes like, you got casting that's 6,000 years old. You got stamping 3,000 years ago. People were stamping coins. So a lot of these processes have been around, but it really takes time to develop the tooling in order to be able to create the shapes. And so if you take a typical, casting, I'm going to cast a part. Realistically, it's going to be 8, 10, 14 weeks or longer, depending on the part, to just set things up and to be able to then crank out parts. And the per piece cost might actually be economical in large volume, but that first part took a few months and tens of thousands of dollars or more. And so what that means is quite often there's a lot less design iteration, a lot less optimization, because you want to get the design over to the foundry so that the tooling can start to be made. And so that's kind of, we all live in that world as engineers and manufacturers, but that is why additive manufacturing is here and getting adoption, is because this is the big problem. And so additive manufacturing's answer is you can mass produce parts via binder jetting without tooling. So let's take a look at that. First of all, what is binder jetting? So this is an additive manufacturing technique using powder metallurgy, where you have a liquid binding agent sprayed, much like a 2D printing press, except this is a 3D printing press, where layer by layer, you're spraying the binder to define what will be solid and what will remain as powder that's then recirculated. Why is this why is this key for mass production? So this is, if you walk the halls of Rapid, you're going to see a few hundred vendors, and everyone's got some 3D printing solution, whether it's for polymer, metals, other materials. But really, binder jetting is emerging. If you look what's happened over the last couple of years with Desktop Metal, some of our competitors, it's really becoming a breakthrough where, given the cost and throughput, it changes the game for additive manufacturing. You can actually make in volume, mass produce a lot of parts. So this is a process that's standing on the shoulders of inkjet printing and a lot of that work around metal injection molding, and I'll talk a little bit about the chemistry of that. And there is attractive part cost, so you can make parts that are very competitive with other mass production processes. So suddenly this opens up, whether you're producing a car and you need 300,000 next year of a certain part, you're going to make that. You can make that with binder jetting, whereas there's no way you could with laser, selective laser melting, powder bed fusion, those kinds of approaches. Until binder jetting arrived, you needed about $1 million worth of equipment to produce 1 metric tons of parts per year, and that's just not kind of a cost structure that mass production, mass markets can take. So what we've introduced, Desktop Metal, is the shop system. The shop system, this is the world's first metal binder jetting system optimized for the machine shop. And I'll talk a little bit about what that means, optimum, for the tailored for the machine shop. So first, this is a scalable and cost-effective way to get going. This is a machine that is, the whole system has been engineered so that you can wheel it right into your shop and put it next to your drill press, your CNC machine, and start with the same team, with the same skill set you have in-house, same facilities, start cranking out parts, the kinds of parts you're making today, and even some parts that you can't make today, and we'll talk a little bit about that. You can reduce lead times. You don't have to have the complex setups of a CNC machine, and you can make fully dense, and I'm going to, over the next few minutes, show you probably a dozen or two parts that you can make. And by the way, this is shipping now. This is here's a bunch of working printers, and they're in Europe. We're starting to ship, and with mass production, mass shipment, volume shipment starting in another few weeks. So this is a working piece of equipment. So first, just we pause on the shop system and talk a little bit about the metallurgy. How is this? What's the process developed? What is the process that this is using? So the approach Desktop Metal has taken is printing system. So this is both the studio that you just saw a great presentation on, and the shop in our production system. This is built around the chemistry and the powder supply chain of metal injection molding, or known as MIM. So why is that so important? Well, MIM, it's a powder metallurgy process. It enables shape complexity, so you can make very complex, sophisticated shape. This is used in a broad variety of markets, and it's because you can use inexpensive powders. This is a de facto way to make a lot of small, medium-sized, complex geometries that are hard to do in other ways. So this is a process that's been around for nearly 60 years now, and so because it's a multi-billion-dollar industry, widely used across a lot of sectors, a lot of applications, there's well-established standards that have been developed, adopted by ASTM, others, and this process supports a very broad set of alloys, literally over 100 different alloys. So you might think, okay, Great, MIM, this works. What does that have to do with 3D printing? Well, these are the giants that we're standing on the shoulders of. And so we've developed printing systems. So the process for MIM is you start with a metal powder and a polymer binder. Then that feedstock is injection molded. So if you think about plastic injection molding, this is a very similar process. There's a creation of a mold, and under pressure, this molten mixture is injected into the mold to define the shape. Well, that mixture is not just plastic, the way it is with plastic injection molding. That mixture is the binder is what melted, this polymer binder, and the metal powder that's not melted, it's coming along for the ride. And so you create the shape, you then do a solvent debind and sinter. That's kind of what you saw with the studio system. And so to put these three things in context, metal injection molding, you got the feedstock, shape creation, debind, and sinter. The studio that you saw a few minutes ago, the feedstock is instead of these pellets, they're rods. Why are they rods? So that you can then put them into ink cartridges or media cartridges and put them into an office-friendly environment. Then there's a debind and sinter step. And then there's binder jetting. Similar process conceptually. You create the feedstock as the powder. The shape creation takes place inside the printer, and then there's a debinder. The process start to finish is there's a print step, so prints layer by layer. Then there's a depowder step, where inside, basically with an air pick, an operator blow off the excess powder where the binder didn't touch, and so then just the shape is what remains. The powder is then over 99% of it is recirculated back, so you reuse that. By the way, a much greener process than casting or other, or even subtractive methods where you've got shavings that sometimes can't be reused, recycled. And then there's the sinter step. The sinter step, you've created the shape. During the sinter step, all of the polymer binder evaporates, and the metal particles, you don't bring it up to melting temperature, but through solid state diffusion bonding, there's necking. The powder particles form grains. Those grains grow to some extent. You can control that, and so you wind up with fully dense parts that are great. But we'll talk a little bit about that. So the features. This is first of all accessible. So this is the shop system, the one behind me, right there, the working one. A working one. There's a dozen of them in the room next door. So this is designed for the machine shop in mind, seamlessly fits into your workflow, and you can produce parts economically, much more economically from many parts than machining or other mass production methods. It is an affordable turnkey solution. There's you can start with a 4-liter, or basically, not that you measure metal parts in liters or gallons, but you can print a gallon of parts, so volume-wise. You can start with a 4-liter, and once you start printing more or larger, just upgrade the same exact system. It's a simple software upgrade. So there's different build boxes depending on your volume needs. Productivity-wise, this is up to 10 times faster than powder bed fusion and more economical. So this is really a lot of parts that you used to. Maybe if you need 5 or 10, you're going to spend $1,000 a piece on a laser powder bed fusion system. You can now make them for $50, $100, and you can make them hundreds per day. And you can really print a build per shift. And so this a build box, and this is roughly a build box, depending on how many parts you're printing, in just a few hours you print them and then move them to the next step. Then you can machine, do post-processing depending on, let's say, so here's a clutch plate. Let's say the outside diameter needed to be not plus or minus 1%, but needed to be within 0.005 of an inch or better. Then you might need to do a finishing operation, but you can save the machinists a ton of time by printing and sintering these near net shaped parts. You have a ton of flexibility in that here's the build volume, you print the parts you want to build. And so there's no tooling required. Every part can be a little bit different, could be very different. So really, mass customization is possible. You don't need to worry, if you're machining things, you don't need to think about producing fixturing, soft jaws. changing setups so that you get into different locations. And so you can even, once there's multiple materials available, you can easily change over. So one day you're printing one material, and then tomorrow you're printing another. And as far as part quality, you can get great precision, great resolution. I'll show a few of the parts, but you can get remarkable with surface finish and build quality, where you can do right out of the. So let's take, here's a parking brake lever. This is no post processing. This part is better than 4 micron average surface roughness, and with super finishing processes, you can get this to 100 nanometers. So there's redundancy built in for both quality and reliability, so that when you're jetting, you have so many nozzles. There's some redundancy built in, so that if occasionally something clogs, you still produce great parts. So what do you get? What do you get from the system? What you get are the resolution, accuracy, surface finish that's similar to castings, fine castings. If there's a critical dimension, then you may need to do some post-processing. So this either gets you the part you need or a near net shape part. So for example, here's an example. This was binder jetted, produced in volume. Normally these Spauger bits are produced with 20 manufacturing steps. Where there's casting, and then there's all sorts of forming. There's like a progressive die situation. With binder jetting, by printing this near net shape part, you go from 20 steps down to 4 steps. You can cut costs significantly. And when you're talking end use parts, every penny counts. So you produce parts with dense, high strength microstructure. Of course, all the things you do with metal parts, whether it's welding, finishing, machining, EDM, heat treatment, etc., all that works. Today, the optimal part size is about sort of 4 inches by 6 inches by a couple inches. So it's parts that fit in the palm of your hand. So I'm going to hold up show a few of these parts. You can also print giant parts. This is a manifold we printed just for the hell of it to see, okay, how big can we print a part? This is a pretty good workout part. I'm not saying you should buy a shop system to then print these giant parts. There's all sorts of development that needs to take place to turn this into a high reliability manufacturing process. But this is what's coming. So today you can print parts that fit in the palm of your hand, and tomorrow you're going to be able to print bigger parts. And there are established standards, because this is using principles in metal injection molding. There's standards around the strength, the reliability. You can go on our website. You can check out the material data sheets. It's great that there's 60 years worth of knowledge, understanding about what MIM steels, whether it's 17.4 or other tool steels, what the behavior of those materials should be, and we meet or exceed those standards. There's 2 basic benefits to getting the shop system. You can save money, you can make money. You save money by eliminating tooling, minimizing tool wear, especially for parts that you might be printing tool steels that are hard to machine. You can reduce labor cost per part. Once an operator sets up the job, it then prints. You don't need to have labor associated with machining and setting up every part. And you do wind up with near net shape parts for which you can reduce the manufacturing steps. The second big category of benefits is you can increase revenue. You can do this for a few reasons. One, you can produce parts you couldn't before. So I'm looking around. I'm going to just hold up a few. Here's a custom, interesting gear. Here's a part that you with all the internal features. This would be have to be assembled from several cast or machine parts. There's a tool slip that would be very difficult to machine given some of the geometry. This is for used in oil and gas applications. You can print hard to machine metals that you couldn't before, potentially. You can make small jobs viable suddenly. You can make 1 or 10 of something, just put it onto the same build that's starting this morning. Just load it up. Before, maybe you needed minimum part quantities. Now, it's much more economical. You can win new business by having to do less no bid kind of things. And finally, by having this capacity, you free up your shop for other projects. So you could do mixed volume of onesie twosies, but a whole bunch of them. You can do batch production, few different parts, or you can do mass production of hundreds of parts once you kind of zero in on the design. So you can really, if you think about the over the life cycle of a part, you need to make a few, then you need to make a pilot run, and then mass production, and then aftermarket. The shop system actually allows you to follow that entire curve. And so here's the shop system in action, printing a whole bunch of parts. I'll show a few. This is just a bunch of examples from across a whole bunch of different industries. What they all have in common is that it's complex geometries. And that's really the kind of things you want to print. If something's easy to machine, or you already have the casting tooling or MIM tooling, by all means, keep doing that. It's more if you have new geometry that you don't want to wait for tooling, or you have parts that are so expensive to make, then this is a great alternative. So I have basically, I think it's 2 slides on applications. So this is a whole bunch of automotive apps. And then in the thing oh, you know what? The watch bezel is not automotive. I'm a moron. This is what happens when you do it in the morning. Okay, everything else is automotive though. So you see here you have parts of the cooling system, drivetrain, suspension, user interface, gear shift knobs. In fact, I'll show a couple. So gear shift knobs printed on the shop system. Here you have the one pattern, but somebody can choose different patterns. Here's a completely different pattern, different finish. In fact, I'll show you just a couple more. We didn't print it in gold, but it is gold plated. And so you can do black nickel plating. So the whole point is you can choose the patterns, you can choose the finish, you can do bespoke parts, you can do mass customization. Really powerful what you can do with a shop system. And then there's a whole bunch of other examples, whether it's medical electronics. You got a stator motor part. So let's see. Here's the stator motor. Here's the downhole tool slip used in the oil and gas industry. Well, what do we have? Well, we got some rotating manifold. Really a lot of, if you can dream up the geometry, there's a pretty good chance you can 3D print it. So we talked about the custom gear shifters. A couple of last case studies. So when COVID hit, there was a shortage of medical equipment. And so one of the things that was needed at a Mass General Hospital was an adapter for ventilators. This part was custom designed, printed on the shop system, so from the time you got the CAD model to the parts coming off the printer was a day, and then in another day they were sintered. So this is a pretty amazing result where you went from no tooling, mass producing these parts, and being packed for the hospital. This is a great example. Another example, a ventilator. A company developed a ventilator and brought it to market in 21 days. Part of that was a new design every 3 days. 3D printing played a key role. You had complex parts with complex geometries. There was no time for tooling. Even standard off-the-shelf parts, nominally off-the-shelf, could not get them off the shelf because of the whole disruption to the supply chain. And so they were just printed. Here's a few of these parts that go into this wobbler assembly. And you know what? Here's the other part. And I'm going to show you this ventilator. Isn't this great for show and tell? Here's the actual thing. And inside, we have just a few minutes here, so I'm not going to power it up, but I could, and I can show you the metal parts working in there. Just think we as engineers like to see the real thing. Last point I'll make is you can now print entire subsystems. So here's a power drill. Inside this power drill right here is a pretty complex transmission system of about 20 different gears. Those gears normally need to be metal injection molded. I'll take a couple out of this nice little gel pack, show them. You see there's a pretty fine detail here. Normally you need to make tooling. This is easily $500,000 worth of tooling before you can start metal injection molding them. Well, with 3D printing, you just print them. And so, the design changes a little bit. You want to customize it, different transmissions for different markets, different models. By all means, you can do that. So that's the story. Now you know everything we know about the shop system, and happy to take some questions.
Oh, thank you, Ilya. We do have a few questions. So somebody is asking if you can print parts like a hinge.
Sure. Let's see. The short answer is yes. Right over here is a. I can actually run over and try to see it, but you know what? I'll do that maybe towards the end if there's time. But absolutely, that's one of the key things is you can print assemblies. You can print things that move relative to each other. So that's another way that you can do assembly consolidation. Turn a bunch of things that you need to produce the parts and assemble them with fasteners potentially into one part. That's one assembly that's actually printed in place.
Okay. One of the questions we have right now is the percentage of new powder to used powder, and how many times can you actually, recycle it to be reused?
So you can recycle. So the powder can be recycled. Over 99% of it is recycled. Virgin powder to new powder. We need no more than 20% new powder, and we're trying to dial in and figure this out. Is this 10%, 15%? But it's remarkable how much you can reuse and how little additional powder you can add and have it be successful. So.
Yeah, so there's a few people asking about the recording. Yes, we are recording this live. It will be uploaded to our YouTube channel, as with other presentations we do. Somebody's asking about the cost. I'm not sure if that's related to the printer or the material. You
know, as a marketing guy, I've been trained by sales to never give out costs. Do you guys want to answer that? You want me to? I'm happy to take a stab at it. I mean, all in the system, it depends on configuration, depends on a bunch of options. It's all in the system is $300,000 to $400,000. All in, I mean the complete system, furnace, printer, the depowder station, all of that. The printer itself is on the order of $170,000, give or take. And the reason somebody might say, well, why would I buy just a printer? There are companies that already have MIM facilities. And because a lot of this technology that's been developed here is using MIM powders, binders compatible with that, it can actually be sintered right in those same furnaces. So for some, it'll be right to just buy the, for example, printer and the depowder station.
Sure. And then, do you know the question about the material cost?
I do. The powder. So I'll answer it in two ways. One is. One way to think about it is what does powder cost, and it's less than $100 per kilogram to powder. The end use cost is a couple dollars per cubic centimeter with the shop system, and so you might have parts that cost a couple dollars to larger parts might be $30, $50. So that's kind of most of the parts fall into somewhere between $5 and $150, depending on size and a few other nesting. So there's a number of variables, but that's the order of magnitude. Just one other thing, for markets where cost is that much more important and the volumes justify it, the production system may be the right fit, where the production system, the material costs, the resulting part costs wind up being 7 or 8 times lower even than the shop system. So then you need to be making millions of parts for it to be justified.
All right, so I'm going to ask you this question, and I hope I don't put you on the spot for doing this. So with traditional DMLS, there's a high percentage of failures. Like I've heard anywhere from 50 to higher % failure. Is desktop metal better than that, or how do you compare to other technologies and their failure rates?
So two ways. I'll answer it. So first, just let me answer it as an engineer. I'm walking around this building and I see, and you know what? I don't know if you can see this cabinet. It's a little dark in here. I'm sorry, it's a little dark, but basically, you got okay, maybe I don't know if this is any better. You know, here. Let's see. Here's see, I just picked up a random bunch of parts. I see literally hundreds of different kinds of parts every day that are being printed with very high reliability. That said, this technology is new, and so we've learned a ton over the last couple of years on what it takes to successfully print via binder jetting parts with you know, good properties, good accuracy. But these are the early days, and so really it's let's look at your application or applications. I've seen tons of parts where yield is very, very high, and I've seen other parts that are just not yet suitable for binder jetting. Every day, the technology, I mean, I'm seeing just as an engineer, it's really exciting, but these are definitely the early days. And so there's tons of different parts that can be made today, but there's also, okay, so for example, what probably can't we make today? Here's a crankshaft. I would not embark on today binder jetting these. But there's a ton of parts that you can. You saw a lot of them. So anyway, it's kind of the answer.
I am going through, there's a few different places to find all the questions. I did have one that came up that I'm not going to read because I don't understand what he's asking, so we'll send that out later in the group. Oh, here's a good one. Will we see lighter materials similar to aluminum, or I think I used to see like a copper part floating around at some point?
Sure. So the short answer is yes, in the fullness of time. So the plans, so aluminum, there are some materials that are, because of the reactivity, you have to be particularly careful, and so there may be different approaches, but for sure, like our production system will handle inerting. So there may be depending on which material, which printing system, but absolutely in the fullness of time. I mean, we've seen copper. The cabinet next door to the one we were just at has a ton of copper parts. So copper's coming on the studio system will be the first printer that it'll be launched on. But sure, copper, steel, tool steels, Inconel, other alloys.
Good deal. All right, so I think we are slowing down, and questions have trickled to a stop. If any of our panelists want to...
I'd say if anybody is producing parts, whether it's functional prototypes or tooling, that would be great for the studio, or mass producing parts, like by the hundreds or thousands per week. Talk to CATI about exploring a metal 3D printing system.
Exactly. If you're even just thinking about it, it's worth the conversation. We're open to talk. We're open to explore applications. And quite honestly, the more interesting the application from an engineering point of view, we love to see it.